Hello, everyone. It is my great pleasure to introduce our first speaker, Professor Delin. He is currently a faculty member at the National University of Singapore. His research focuses on numerical linear algebra and scientific computing. Today, he will present his latest insights on numerical computation for non-negative matrix of factorization. Let's welcome.
Thank you. First of all, I want to thank you, the organizer, for invitation. Also, thank you, Professor Bear, for coming to my talk. Okay. Recently, in the recent 10 years, I work on numerical linear algebra with application to machine learning. Okay. Today, I want to talk about my work on non-negative matrix factorization. A non-negative data matrices, we know have found a lot of application. For example, we can find some application in this book, environment data analysis. This book is written by two engineers, not mathematicians. The non-negative matrix factorization was first developed by these two guys. Non-negative data matrices have also found application, for example, in image processing, text documentation by informatics, because the data matrices in such application are usually non-negative. So non-negative matrix is a very active research topic. The definition of the non-negative matrix factorization is very simple. Suppose we are giving a matrix A, M by M matrix A. Also, we are giving a low rank R. Of course, R should be much smaller than the size of A. I mean, R should be much smaller than N, also much smaller than M. Non-negative matrix factorization is to find two low rank non-negative matrices. U star in M by R, V star in M by R, so that U star, V star solve this minimization problem. So this is called a non-negative matrix factorization problem. Now we denote the columns of U by U1, U2, UR, columns of V by V1, V2, VR. X is non-negative. This means all elements of X are non-negative. As I mentioned before, a non-negative matrix factorization was first induced by these two engineers in this paper. Then it was extended in a Nature paper published in 1909. Also in this Nature paper, a very famous algorithm called MEU algorithm is developed. Now we can see these two papers are very high citation. Very high citation. Now, non-negative matrix factorization has become a very powerful tool for non-negative data dimension reduction. They also found application in a loss field. For example, image processing, image clustering, data mining, signal processing, and so on. In non-negative matrix factorization, the number R of basis vector in U is much smaller than the dimension M, also the number N of data points, which reflect the dimension reduction. The non-negativity of U and V somehow play very important role in application because it allows one to extra meaningful and interpretable components in non-negative data set. So this means in the application of non-negative matrix factorization, usually the data matrix should be non-negative. Well, for mathematical study, okay, somehow we just consider general matrix A, okay, not non-negative matrix A, okay. Non-negative matrix factorization is NP hard. So almost, okay, all existing algorithms just want to find the local solution or stationary point, okay, somehow it's harder to find the global solution. Okay, now we want to talk about the dimension reduction. The dimension reduction is to represent each data points as a linear combination of a small number of basis vector. Okay, suppose we have n data points, A1, A2, An in Rm. Then dimension reduction want to find the basis vector U1, U2, Ur such that each data points Aj can be well approximated by linear combination of the basis vector U1, U2, Ur. I mean, we can approximate Aj by the summation Ui, Vji, I from 1 to R. Okay. Okay, now let's look at this figure. Okay, in this figure, we just approximate two-dimension data points by one dimension. Okay, one dimension vector U1. Okay, this is line generated by the vector U1. Okay, similarly, we also can approximate three-dimension data points with a two-dimension subspace generated by basis vector W1 and W2. Okay, now according to our definition, suppose we approximate Aj by the linear combination of U1, U2, Ur, then this means we can approximate the data matrix A by U times V transpose. Okay, each column of A is a data points. Okay, each column of U is a basis vector. Each column of V transpose contains the coordinate of data points in the basis U. As I mentioned before, rank R, low rank R should be much smaller than M and N. Okay, now we want to consider a simple example. Okay, we apply the method of built-in function. Okay, this is a method of built-in function. Okay, based on the algorithm in this paper, we apply this built-in function to our fixed data set CBCL. Okay, this is our CBCL data set. Okay. Now this data set contains 2,429 fish images. Okay, of course for of the same resolution. Okay, each one just is 19 by 19. So now if we construct the data matrix A, okay, so that each column of A corresponds to to an image. Okay, of course then we can vectorize. Okay, so A just is a matrix with M 361 and 2429. Okay, now suppose we choose R equal to 20. Of course we can choose different R. Then by MATLAB, then we can compute the matrix U. Then we get the columns of U are basis image contain some very important facial features such as eyes, nose, lips. Then UV transpose is a low rank approximation of matrix A. Okay, if so, then let's consider what means the dimension reduction. The original data contain about 900,000 elements, while the reduced data contain just 60,000 elements. Okay, now this is matrix A. Okay, this type, this is U. Okay, now we approximate by U V transpose. Okay, this is the original data set. Okay, then this line 20 basis image. Then this line, okay, we get the approximate image UV transpose. Okay, for this example, because we choose R equal to 20, the approximation looks acceptable. Where if we increase R, then we get a better result. non-negative matrix factorization has been studied extensively. Okay, there are a lot of numerical methods. Okay, for example, very famous MEU method. Also very powerful method called HAS method. Okay, also this one we develop. Then we also have some method called active set method developed by Heisenberg. He's a same fellow. Okay. Also this method, BP method, also is developed by Heisenberg. Also the gradient type method, Newton type method, individual point method. Actually, all optimization technique have been applied to non-negative matrix factorization problem. Okay. Well, now I guess most of you know in optimization, gradient type method, Newton type method, individual point method usually are very powerful, very popular, right? Well, unfortunately, such very powerful optimization method are not so efficient for non-negative matrix factorization problem. Okay, mainly because in non-negative matrix factorization problem, there are two constraints: u greater than 0, greater than or equal to 0, v greater than or equal to 0. Okay, as a result, such a powerful optimization method, are not efficient as we hope. Okay. Yeah, okay, now I want to introduce the very famous method, MEU method. Okay, MEU method looks very simple, okay? Somehow we can consider MEU method as a PG method, okay, in optimization, okay? The elements of matrices U and V are all updated, okay, with individual select step size. Okay, now suppose A is a non-negative. Also, we denote SU, the matrix of step size for U, then SV transport, matrix of step size for V transport. Now, suppose we apply the PG method to this optimization problem. Okay, then we have this standard scheme. Okay, this standard scheme. Okay. Okay, then we just choose particular step size for each element. Okay, now we choose particular step size. Okay, this is the step size for the element of U. This step size for the element of V transport. Okay, now if we choose step size like this, then the numeric scheme we just showed before reduced to these two formula. Uij equal to Ui is updated as Uij times AVij over UV transport Vij. Similarly, we have the formula for V for element of V. Okay, now very clear. Okay, so these two formula very simple, right? Okay. Also, we can see if A is non-negative, then Uij is non-negative, VPQ is non-negative. Okay. This reason why we assume A is non-negative. Okay. Okay. The main advantage of this method is that it is very simple, right? Okay. Also, now we know under the multiplication updating rule, the objective function is non-increasing. Okay, so the sequence of the objective value is convergent, but so far nobody knows whether it converges to a stationary point of our non-negative matrix factorization. Okay, so far nobody can show this result. Okay, okay. Also, another main disadvantage is that the MEU method converges very slow. Okay, because this method converges very slow, so in practice, okay, not often used. Okay. Okay. Okay, next we want to introduce BCD type method. Not consistent. Okay, yeah. Okay. Now most of this method can be considered under the BCD framework. Okay, on the BCD framework, U and V are partitioned into different blocks. For example, elements or columns, multi-columns, or whole matrix. Each block is updated by as the optimal solution of the corresponding subproblem, which is result from fixing all the other blocks. Of course, different partition lead to different methods. For example, these two non-negative alternating non-negative least square framework MBPP method view U and V as two whole matrix blocks. Well, ARK and AS method view K columns of U and V as a block. HAS method regard each column of U and V as a block. Okay, now we want to talk about HAS method. This method is very powerful, very popular now. HAS method is one of the most powerful methods so far. This method was developed independently in these two in this paper and this PhD thesis. Now we consider the objective function as a function with variable v1, v2, vr, u1, u2, ur. Then we update uj and vj by solving subproblem 3 and subproblem 4. So this means for I from 1 to r, now we update ui by solving this this minimization problem. Then update uj by solving this minimization problem. Now we know if we can solve this minimization problem and this minimization problem exactly, then the BCD method, the related BCD method should be very powerful. So now the key is how whether we can get exact solution for subproblem 3 and subproblem 4. We need to wait. Now we can show this a very simple lemma. Suppose we have a matrix G and a non-zero vector V, then the solution to this minimization problem is given by this formula. Here plus means if the element less than 0, then we change it to 0. Similarly, we also have this result. By applying lemma 2, then we get the exact solution for subproblem 3 and 4. So as a result, we have this HAS method. Each step we apply this formula to update VI, also update UI. So the formula looks very, very simple, right? This is reason why this method is very fast, also very efficient. Because in each step we solve the subproblem exactly. Also we have very simple formula, so the updating process should be very fast. Now on the convergence. For HAS method, there are two different kinds of convergence results. One is called weak convergence, another called strong convergence. Now suppose UKVK is a sequence generated by HALS. Now we also assume each column of UK and VK are non-zero throughout all the iterations. Then the sequence FUKVK is decreasing, converging to a limit value F star, and every accumulation point of the sequence UKVK is a stationary point of non-negative matrix factorization problem, also KKT point. This is called a weak convergence. Again, for strong convergence, we should have a assumption. There exists a constant L greater than 0 such that VIK non greater than or equal to L for I from 1 to R, and for all K, Then under this assumption, then we can show the sequence UKVK given by HAS method is a Cauchy sequence, and through converging also converging to a stationary point of non-negative matrix factorization problem. Okay, so far this is the only strong convergence results. Okay, also we do know how to remove this assumption. Okay, how to remove this assumption. Okay, so far we do know. Okay, this result is first proved in this paper. Then we simplify. Okay. Okay, now we want to consider how to generalize HAS method. Okay, now we know HAS method update only one column of V or U in each updating step. In order to improve this method, now we can consider to update more columns of V or U in each updating step. Okay, this consideration leads to a new method we call ARK-NLS method. Okay, now we partition U as a blocks. Okay, U1, U2, UQ, V, V1, V2, VQ. Okay, each block, okay, contain K columns. Of course, the last block may contain only K minus 1 column or K minus 2 column and so on. Okay, then we consider the objective value function. Okay, as a function for the variable. Okay, U1, U2, UQ, V1, V2, VQ. Then by BCD idea, now we just update each block UIVI by solving the subproblem 6 and 7. Okay, now the key is whether we can solve subproblem 6 and 7 exactly and very quickly. Okay, if we can solve these two subproblems exactly and also very quickly, then the resulting new method should be powerful than HAS method. Okay, so now we want to talk about how to solve subproblem 6 and subproblem 7. Okay, now because the subproblem 6 and 7, okay, can be written like this. Okay, can be written like this. Okay, well now when we update VI, we have the corresponding G and B. When we update UI, we have the corresponding G and B. Okay. So in order to find the closed form solution for the subproblem 6 and 7, we only need to find the closed form solution for this subproblem A. So our main question is, can we compute the closed form solution of this non-negative least square problem? Okay, if K is 1, then it's easy. Well, if K greater than 1, somehow this non-negative least square problem is not so easy. Okay, now the problem A can be decoupled into independent non-negative least square problem with single right-hand side vector like this. Okay, well, this kind of minimization problem also can be written in a unit form. Okay, minimize gy minus b with constraint y greater than or equal to 0. Okay, so now we just try to solve this minimization problem. Okay, how to solve this minimization problem? Okay, now we know if k is 1, we know how to get the solution. So naturally, now we want to know what is the relationship between rank k n s problem and rank k plus 1 and s problem. If so, then we can reduce rank k problem to rank k minus 1, then rank k minus 2, finally rank 1 problem. In such a way, we can get the solution. This is the main idea. Okay, now we can show this reduction property. Suppose we have m by k matrix G, two vector gk plus 1 and b both in Rm. Okay, now we suppose these two matrices, okay, are of full column rank. Also, we denote the unique solution of the rank k minimization problem by this notation SGB. Now we consider this rank k plus 1 non-negative least square problem. Okay, then we have this formula. This means Okay, in order to compute this rank 1, rank k plus 1 problem, now we only need to solve two rank k non-negative least square problem. This one, this is another one. So this means if we can solve rank k non-negative least square problem, then by using this formula, we can get the solution of any rank k plus 1 non-negative least square problem. Okay. Okay, so now we just found out the relationship between rank k plus 1 NAS problem and rank k NAS problem. Okay, now we can. Yeah, okay, now we apply this relationship to the case k equal to 3. We apply to the case k equal to 3. Okay, now suppose we have n by 3 matrix G. Also suppose this matrix is a full column rank. Okay, then this formula, okay, gives the exact solution for this minimization problem. Okay. Yeah, okay. So now we get the closed form solution for rank 3 non-negative least square problem. Then we apply the results to to our problem. Okay. Now in a similar way, we also can consider k equal to 2. Okay, k equal to 2. Then we also have the closed form solution. Okay. Now as usual, we just partition U and V as block U1, U2, UQ, V1, V2, VQ. Of course, okay, the last block we need to do a special treatment. Okay, maybe the columns of last block has 2 columns, 3 columns, or 1 columns. Okay, now for notation simplicity, okay, we denote the columns of UI as U1, U2, U3, VI as V1, V2, V3. Then we want to find out the closed form solution for our subproblem. Okay, so we have this result. Okay, now suppose UI n by 3 also full column rank. Then the unique solution of this rank 3 non-negative least square problem, okay, is given by this formula. Okay, by formula 15. Of course, the formula looks a little bit complicated. Okay. Again, as I mentioned before, okay, this theory is based on the assumption, okay, R over 3 is an integer. If R over 3 is not an integer, then we need to do some special treatment, okay, on the last block of U and V. Okay. Okay, based on the results we just derived, so we have the following method we call ARK-NAS, with k equal to 3, Now, in each updating step, we need to solve rank 3 non-negative least square problem 6 and rank 3 non-negative least square problem 7. Okay. Also, okay. Now we know how to solve this subproblem, right? Okay, on the convergence. Okay, similarly, we have the similar convergence results. Okay, for example, for the weak convergence. Now suppose the sequence UKVK are generated by ARK-NAS, okay, with k equal to 3. Okay, now we assume the involved UI and VI are of full column rank throughout all iterations. Then the sequence FUKVK is decreasing, also converging to a limit value F star. Moreover, every accumulation point of UKVK is a KKT point or stationary point of our non-negative matrix factorization problem. Okay, similarly, we also have the strong convergence results. Okay, with the similar assumption. Okay, also the proof is quite straightforward. So I only show the convergence for the weak convergence results. Okay. Again, in this paper, a lot of numerical experiment are given. Okay, according to the numerical experiment given in this paper, now we know these two methods, HAS method and BPP method, are the most effective in the sense HAS method is very fast, while BPP method is very accurate. Okay, if we consider the residue. Okay, so now we just show a numerical example to compare our new method with our new method with HAS method and BPP method. Also, this is another method. Okay, okay, this method. Okay, something nobody cited this method. Okay, well, later we found this method, so we want to also compare with this method. Okay, now we consider two data sets. Okay, one is very sparse, one is very dense. Okay, now we measure the accuracy using the residue. Okay, A minus UV transport F none over A F none. Okay, now we have these two graphs. Okay, okay, this red one is given by the new method. Okay, the red one is given by the new method. Okay, now our numeric example, okay, lead to some observation. For example, okay, the new method, okay, achieve good approximation error in a fraction of the time taken by other method. The main reason for the good performance of the new method is due to computation efficiency. Okay, in particular, okay, the new method is able to perform thousands of iterations in the same time as it takes BPP or HAS method to perform the tens. Okay, this reason why the new method performance are very good. Okay. Also, of course, we know given enough time, the other algorithm, for example, BPP method, may find a good solution. But okay, the CPU time should be very high, in particular for a large value R. Okay, our numeric experiment also show the ARK method achieve a good balance between accuracy and computation efficiency, and discover a good approximation much faster than the other method. So the new method provides state-of-the-art performance in terms of the computation accuracy and CPU time. Okay, well, one question is why we only consider k equal to 3, not consider k equal to 4 or k equal to 5 and so on. Okay, the reason is, okay, if we consider the big K, okay, the closed form solution becomes more and more complicated. This is one reason. Another reason, okay, Okay, now in here we have an assumption. Here we have an assumption. Okay, the involved UI and VI are of full column rank. Okay, if k equal to 3 or k equal to 2, okay, now if we consider k equal to 2 and k equal to 3, well, even this condition is not satisfied, then we know how to handle. Okay. Well, if k equal to 4 or k equal to 5, we don't know how to handle this singularity problem. Okay, this is another reason why we only consider k equal to 3, not consider k equal to 4 or k equal to 5. Okay. Because we know if k equal to 4 or k equal to 5, the resulting accuracy should be better. Okay. Well, now in particular, we don't know how to handle this singularity problem. Okay. Okay. This is the reason why we only consider k equal to 3. Okay, next we want to consider a special case of non-negative matrix factorization. We call symmetry non-negative matrix factorization problem. Okay, now suppose A is symmetry. Then we know if A is symmetry, then we should do a symmetry low rank approximation, right? Okay, so this means if A is symmetry, then in the classic non-negative matrix factorization, U and V should be satisfied U equal to V, so that UV transport equal to U transport. So this means we approximate symmetry matrix A by another low rank symmetry matrix U transport. As a result, the symmetry non-negative matrix factorization problem can be defined, okay, by minimization problem 25. I mean, we just minimize A minus U transport F non square. which constraint U M by R matrix and U non-negative. Okay, when I equal to 1, this minimization problem, we call rank 1 symmetry non-negative matrix factorization problem. In symmetry non-negative matrix factorization problem, the matrix A usually is a similarity matrix, while the ij elements is a measure of the similarity between the ith and jth data point, and so is non-negative. Also the low rank information in the similarity matrix play a very important role for data clustering. Of course, symmetry non-negative matrix factorization has been found application. For example, has been used in many different settings, including graph embedding and clustering. Similarly, symmetry non-negative matrix factorization problem also has been studied by Alert's research. So also Alert's numerical algorithm can be found in the literature. For example, instead to solve the symmetry non-negative matrix factorization problem directly, now we can solve this minimization problem. This is the typical approach used in optimization society. Here, parameter R, alpha greater than 0 is a parameter for the trade-off between the approximation error and the difference of U and V. Then we can apply alternating non-negative least square method or HAS method to solve this minimization problem. In such a way, we have the so-called symmetry ANLS method and symmetry HALS method. Another approach often used in optimization society is we transfer the symmetry non-negative matrix factorization problem to this minimization problem. Here, tau greater than 0 is a given constant. Vi just a column of V. Then we can apply ADMM-like method to solve this minimization problem. Now what are the difference? If we consider this minimization problem, no matter what method we use, the convergence is the most convergent to the KKT point of this minimization problem, not the original symmetry non-negative matrix factorization problem. Well, if we consider to solve this minimization problem, there is a very good theoretical result. There is an upper bound for tau. So that the KKT point or stationary point of this minimization problem, are the KKT point or stationary point of the original non-symmetry non-negative matrix factorization problem. Well, now the problem is how to choose such parameter tau or parameter R. Actually, almost this algorithm involves some parameters which will significantly affect the accuracy and the validation of the related method. Well, so far, there is no general we can use to select a good parameter for different method, also for different data set. This is the big problem for such method. Well, based on this observation, naturally we hope whether we can develop a numerical method without any parameter. So now we introduce a new method, developed in this paper, called PHAS method for symmetry non-negative matrix factorization problem. Again, to do so, now let's consider this rank 1 symmetry non-negative matrix factorization problem. Now this problem looks very, very simple, right? Well, unfortunately, this minimization problem has no closed form solution. At least so far, nobody know how to get its closed form solution. Okay, because of this reason, so the popular HAS method, okay, for non-negative matrix factorization problem cannot be generalized directly to symmetry non-negative matrix factorization problem. Okay. Well, now what we can do? Okay, now we consider the following idea. Okay, now I updated the columns of U, U1, U2, UR okay, as follows. Okay, now for I from 1 to R, now we denote AI equal to A minus summation UK transport K not equal to I. Then we try to find the UI, such that AI minus UI transport F non square less than A minus U transport F non square. So this means we try to find the UI so that the resulting the objective value is decreasing. Okay, is decreasing. Then in such a way we can get the sequence UI, okay, which satisfy FUI plus 1 less than or equal to FUI. Okay, this means the objective value is decreasing, so convergence, right? Okay, so now this means we try to upgrade the UI, so which guarantees the convergence of the sequence of objective value. This is the idea. So now the question is how to find such a UI. Okay, now in order to find such UI, we need to consider this rank 1 symmetry non-negative list square matrix factorization. Okay, so now we focus on rank 1 on symmetry non-negative matrix factorization problem. Okay, D minus U transport F non square. D is symmetry. Okay, D is symmetry. Well, now U should be non-negative. Okay, now let's recall this result. Okay, now suppose D is given, U is given, U is non-zero. Then the solution, unique solution to this minimization problem is given by this vector. D transport U plus over U transport U. Okay, according to these results, naturally we may consider to update U using this vector. Well, unfortunately, okay, this updating on U does not always lead to the reduction of FU. I mean, if we update U by this vector, then the objective value may not be decreasing. Okay, so this means we cannot update U using this vector. Well, then what we can do? Okay, now motivated by the gradient descent method. So now we consider the convex combination of the original U and this new vector. Okay, this step is from the idea for gradient descent method. Okay, then we get U new equal to U plus lambda D, D equal to D transport U plus over U transport U minus U. Okay, now if we look at this formula, then D can be considered as a search direction, where lambda is the step size on this search direction. Okay. So next we need to consider whether D is the descending direction. If so, then on this descending direction, how to choose a good appropriate step size lambda. Okay, now we can show D is a good descending direction. Also, we can show D equal to 0 if and only if U is a stationary point of rank 1 symmetry non-negative matrix factorization problem. Okay, so this means if D is 0, then we can stop iteration because we get the stationary point already. Okay, then there is one question: why we not use the gradient descent direction? Why we not use gradient descent direction? Okay, now we write down the gradient descent direction of for minimization problem 29. Okay, this is the gradient descent direction. Now we found, okay, when there exists an index I such that the ith element of u equal to 0 and the ith element of du less than 0. Then the ith element of minus delta fu less than 0. Then this means in order to guarantee the non-negativity of u minus lambda delta fu, the step size lambda must be 0. Okay, so make no sense. Okay. Also, okay, in our numerical experiment, okay, these two often happen quite often. Okay. So this is reason why the gradient descent direction cannot be used. Okay, let's consider how to choose appropriate step size lambda. Okay, now let's denote g lambda equal to fu plus lambda d. Okay, d is non-zero we defined before. Then g lambda is a decreasing function on the interval from 0 to lambda star. Well, lambda star is the smallest positive root of the function g prime lambda equal to 0. Also, we can show lambda star exists. Okay, so we only need to solve the smallest possible solution for g prime lambda equal to 0. Well, g prime lambda is a cubic polynomial, so we can find its smallest possible solution very easily. For example, we can use this method very quickly. Okay. Also, we know lambda between 0 and 1 is necessary in order to guarantee the non-negativity of the u nil from here. Yeah. Okay. This non-negative, this non-negative. So lambda should be between 0 and 1. Okay. So now we combine this condition and these results together. Then we know we can choose lambda as the minimum value of lambda star and 1. Okay. So now we just choose lambda to be minimum value of lambda star and 1. If so, then fu nil equal to fu plus lambda d less than or equal to fu. Also, u nil greater than or equal to 0. Okay. Also, we have one more result. Okay. Now we found this difference. Fu plus lambda d minus fu is bounded by this number. Okay, now very clear, if d is non-zero, then this means fu plus lambda d less than fu strictly. Okay, so in each iteration, the objective value reduce strictly. Okay, then we can apply the results we just showed to a symmetry non-negative matrix factorization problem. Okay, so now we need to update the UI based on this rank 1 symmetry non-negative matrix factorization problem. Okay, so now we have this is AI A minus summation UK transport k not equal to I. Okay, now we can denote E equal to A minus U transport. Then from E we get AI equal to E plus UI transport in order to save the computation cost. Okay, then we can compute DI. Okay, then we compute the step size lambda. Okay, after that we update UI equal to UI plus lambda D. Okay, then next we compute new E just equal to AI minus UI transport. Also, in order to save the computation cost, we also need to repeat the we also need to avoid the repeated calculation. Okay, such step just to avoid the repeated calculation. Okay, then we have this method we call PHAS method. Okay, now the computation cost of each iteration is about big O n squared times R. Now we also ask the question whether we can reduce the computation cost of each iteration further. Well, we cannot do. Okay, now another question. Okay, somehow we see we need to know whether the convergence or convergence to the KKT point. Then the question is how to measure. How to measure whether your method converging to KKT point or stationary point. Okay, now we have these results. Okay, for the classic non-negative matrix factorization, actually we have the similar result. Okay, now because we know the KKT point and stationary point for symmetric non-negative matrix factorization problem are equivalent. Okay, now we show U star is the KKT point of our symmetric non-negative matrix factorization if and only if this equation hold true. Okay, if and only if this equation hold true. Okay, now according to these results, we can define the gap U, right? We can define the gap U. Okay, now if we look at this result, then we know gap U is a practical indicator we can use to measure the optimality on KKT point. I mean, if gap U converging to 0, then this means the sequence, our sequence, okay, converging to a KKT point, right? Okay, so we call gap U as the optimal gap. Okay, now for the convergence, okay, we can show, suppose UK the sequence generated by PHAS method, then the objective value, the sequence of objective value is decreasing, converging to a finite number F star. Also, every accumulation point of UK is a KKT point or stationary point. Okay. Well, for symmetric case, we have weak convergence. Now we cannot show the strong convergence. Okay, okay, the proof become much more difficult to compare the classic case. Okay, also we can show UK, okay, given by PHAS method, okay, satisfy gap UK converging to 0. Of course, this means UK converging to the KKT point or stationary point. Okay, now we show our numerical results. Okay. Okay, now we compare our new method with these two methods, symmetry HAS method, symmetry ANS method, and Newton-Table method, also two BCD method. Okay, the reason is as we know such method have been shown to be competitive with other existing method. Okay, now we consider two data set. Of course, in our paper, you can find many different results for different data set. Okay, okay. Now we consider these two data set. Also, the parameter. Okay, the parameter for the method we compare are from the authors. Okay, from the authors of the method. Okay. Okay, now we just consider low rank R 20. Now we measure with the relative error, also the optimal gap and the CPU time. Yeah. Okay. This graph shows the results on this data set. Okay, on this data set. Okay, this line is given by the new method. Okay, this line is given by the new method. Okay, this is for the relative error with a CPU time and the optimal gap. Okay, now we consider the optimal gap. Okay, now very clear for new method, the optimal gap converging to 0 very quickly. Or this method also converging to the optimal gap also converging to 0, a little bit slow. Well, these two methods, this method, very clear. The optimal gap, cannot converge into 0. So this means such method cannot converge to KKT point or stationary point. Okay, for another data set, we have similar results. Okay, we have similar results. Okay, we have similar results. Okay, new method converging to the KKT point very quickly. This method also converging to KKT point. Well, this method, again, cannot convert to a KKT point. Okay, now Based on our numerical experiment, we can conclude the new method converge fast on the relative error and optimal gain in general. Although the new method is more stable compared with symmetry HAS method and symmetry ANLS method, also other method. The reason is okay, the related parameter R are very sensitive, sensitive for the relative residue for the optimal gain. Okay. Another reason is for different data set, we don't know how to choose a good parameter. We don't know how to choose. Okay. For data set 1, maybe we can choose good parameter R equal to 1. Then if we change the data set, then the alpha value also must be changed. Well, how to change we don't know. Okay, we don't know. Okay, so also according to our numerical results, okay, the optimal gain is a very good measure for KKT point. Okay. Yeah. Okay. Now I stop my talk. Thank you very much.
Thank you for the speaker. Any questions or comments from audience?
Okay. Thanks for the nice talk. I have a theoretical question. We know for the non-symmetric non-negative matrix factorization, if we choose the R as large as possible, there must be the objective function must be 0, right? Because we can just like U equals A and V equals identity.
No, not necessarily. Okay, if A has a exact decomposition A equal to U V transport, then yeah, right. Well, if not, then not right.
Okay, so this is not my question. I mean, even for the non-negative symmetric matrix A, is there any criterion for the existence of the symmetric non-negative matrix factorization?
Now, as I know, there are a few results, not too much.
Okay.
Yeah.
Okay, thank you.
Also, some conditions are very strict. No general results. No, I mean, no general necessary and sufficient condition for the existence. So that A has exact decomposition, non-negative matrix factorization. Yeah. Yeah. Thanks.
In the beginning, you mentioned for the symmetric case. So one of motivation for your work is try to avoid this parameter alpha. You try to do this, this symmetric.
Yeah, this is our motivation. Yeah.
Yeah, but in the end, why this alpha coming in again or different alpha? Somehow I lost it.
Okay. Now, because in our numerical test, we compare with this method.
Yeah.
Okay, in this method, alpha is involved.
Okay. Oh, so that was in your conclusion.
Yeah. Okay, our conclusion on alpha is for this method and also this method, not for our method. Yeah. According to our experiment, okay, very difficult to choose the appropriate parameter for tau for alpha.
Okay. Any other questions or comments from audience? If not, let's thank for the speaker again.
And thank you very much.